Yeah, I don't think we should do that. I did fix some stuff.
It's like when I do the broadcast on this just so it's like I feel like I'm understanding the broadcast and it's I don't know why it's looking up. But it's also like not running on my own computer, so I'm like, my computer.
No, yeah.
I was just
Sorry for that.
I'm just curious, like I haven't talked to anyone else who's like this part of it.
Yeah, I think it's starting. Yeah, it was like crap.
Oh, really?
It was like
Oh, yeah, that's what's happening. Like a lot of people I know who were like that in last year. Yeah, it's fine. Yeah, I was like, oh, I should take as many classes as I want to take while I still can for free.
Yeah.
Hello, everybody. Good to be here. Okay, let's get started. So, a little late today, I apologize for that. You hopefully got the notice about there having been a student in this class a week ago on Tuesday that has now tested positive for COVID. You either got that through the contact tracer or I posted this announcement. So, there are certain protocols that the university has asked all of you to follow in those cases, whether or not, there are certain protocols that you're vaccinated, certain protocols that you're unvaccinated. I just encourage you to follow those. Besides that, any questions about that or about where we're at right now in the lectures or the homework?
I have a question for office hours.
Okay, perfect. That'll be the first. No one has come to my office hours yet. Okay, cool. Well, let's get started. So today we're going to talk about convolutions. So, we worked our way through some basics about neural networks, about how we optimize them, how we measure, like how we define tasks, at least simple tasks like classification, how we measure how well we're doing on those. And we've been using images as like kind of prototypical data type for all of that discussion. And we've been using, we've talked about like fully connected networks here in the context of like say a small images like that are in CFAR 10, right? So they are 32 by 32 by 3. So those are relatively small images, but images are typically much larger than that. The ones coming off your camera are, in terms of resolution, have there's a lot of pixels there, and in general, if you wanted to define a fully connected network there, you'd have a lot of operations. It would be a very large matrix mapping you, say, like from the input space to like the first hidden layer, and it would surprisingly be prohibitively expensive to do. So what do we do about that? So one of the approaches for dealing with that is to use convolutional layers, and neural networks made out of convolutional layers are known as convolutional neural networks, or CNNs. And so we'll get into that now. So because I'm a bit behind, you can read these slides are posted, so you can read these here. Just know that there's some history here, right? So in 1957 there was a paper published on what's called Perceptron. It's probably one of the earliest publications that use something that looked like like modern neural networks. It had a kind of activation function here that summed up the inputs coming in with weights as a bias term, and then it had an output of 1 or 0. Again, taking its inspiration from like actual neurons in the brain. And this was implemented in analog hardware like this, you can imagine. And I don't know what problem, I don't know what all the problems it solved, but this thing was taught to recognize letters of the alphabet. So not too different from like our MNIST data set where we that's a very typical data set that people use when kind of testing out convolutional ideas, and those are the 10 digits for a typical number system. That was in the 50s. In 1980, you get something that looks like a hierarchical structure of convolutional networks or convolutional operations. For whatever reason, this thing was called the neo-cognitron. I don't really have any sort of reason for why that would be. Just it was, everything was these days kind of inspired by things like the human brain, like neocortex, like cognition. You get these kind of fancy names, always ending in tron for some reason. In 1986, we part of talked about last time, but you get a paper that popularizes backpropagation. It certainly wasn't the first description of it, but this is a paper one of the authors is Jeff Hinton, who in 2018 won the Turing Award, along with Jan LeCun and Joshua Bengio for their pioneering work in what is now kind of modern deep learning. But so you get in the 80s, you get kind of a popularization of the backpropagation algorithm for training neural networks, and then in 1998 you get a couple of really big names like in modern machine learning, in modern neural networks. Jan LeCun again, just one of those people. Joshua Bengio again, one of those people, along with Jeff Hinton, who won the Turing Award. Leo Bouteau didn't win that award, but has certainly published a number of really influential papers. Anyways, what you get here is a convolutional neural network that's known as LayNet 5, I think because it's 5 layers. Lay from LeCun's name, and it's really kind of like the earliest kind of modern convolutional network. And this thing again was trained to recognize letters of the alphabet. But it has the kind of structure that you see in modern convolutional networks, where you start from input. There's a convolutional layer operation that transforms this input into another tensor. That there's these ideas of subsampling or pooling that reduces the spatial dimensions or the resolution of these tensors. Applies convolution, alternating between that and the subsampling or pooling idea, and then eventually you take whatever this final tensor, flatten it out, have a couple of fully connected layers, and then have that becomes like an output. For example, scores over your alphabet, and it was trained via backpropagation. So 1998, this is like the state of the art. We can recognize handwritten digits.
Yep. So what's the difference between the second and third slide, if you go back to? Yeah. What's the difference between this one here?
Yeah, this one, like the convolutional operation is not like the modern convolutional operation. It's a kind of different operation, but we won't spend time on it because it's on behind and it doesn't really matter all that much. This is what matters here, and we'll talk about it today. Then what happens is, so if you know something about the history of like neural networks, they've kind of come and gone like in popularity. There were times where they became popular, like in 1998 with this paper. So in '86, backpropagation, people get really excited about neural networks. Here's an efficient algorithm for training them, and then they realize they don't work very well, even though you know how to train them. So they kind of go out of favor, and it's like one of those things where if you're publishing papers in neural networks, and people kind of think of you as backwards. It's kind of like if you use sigmoids as activation functions. That people think of you as backwards. And then there's some success here. So it kind of becomes popular again, but then people realize like, well, yeah, like that one example worked, but it doesn't really work for anything else, so not that, not that great. And again, kind of fall out of popularity. But people like Jeff Hinton and Joshua Bengio, McLean kind of kept working, doing research in this area, publishing in this area. And, in the mid-2000s, Jeff Hinton's group at the University of Toronto starts kind of doing things a bit differently, and has really what are probably like the first really deep neural networks that are in this autoencoder kind of format, where the idea is you're learning to basically compress an image into some very small number of factors that then regenerate the image. Maybe not perfectly, but most of the image can be kind of reconstructed from this. And it was done using what are known as restricted Boltzmann machines, and so these RVMs, and so there's like a pre-training step for all of this, kind of a greedy layer by layer pre-training, but this tended to work, and gave you really great kind of like compressions of images, and so now people are kind of looking into neural networks again, starting in the mid-2000s. Then, really, everything for deep learning kind of really takes off, and I already mentioned this in a previous lecture, with this network right here, which wins the Imagenet competition. And we're going to spend actually like the next couple of weeks kind of going through the history of the Imagenet competition for computer vision. It starts in 2010. The first couple of years, there are no neural network submissions, but in 2012, there are a bunch, and this one wins by like a long shot in terms of like the amount of improvement over the previous year's winner. And this is known as AlexNet because of the authors here. And if you look at this, we'll spend time going through this, so don't get too worried about it just yet, but you might notice that like this looks like a really weird image, like it's cut off at the top. Like I maybe made a mistake when I put it up there. It turns out that this is how, in the paper in 2012, that image was cut off like that. And so forever, this is the image that goes along with AlexNet, and it's, like for some reason, the top's cut off of it. So it's just one of those artifacts of history. And now you know. You might also think it's weird that there's like kind of two things going on here, and as we go through convolutional stuff, like you'll figure what that is, but this is a kind of efficiency that was done here, where they split up the filters across two different GPUs. This was like a way of them being able to use two GPUs at the same time. Sure. Anyways, so 2012, AlexNet wins this Imagenet object recognition competition, and basically from then on, like the kind of the modern era of deep learning begins. So it's only 9 years ago, but so much has happened in that time, right? So, like we're going to kind of slowly go through convolutions, right? But like even convolutions, interestingly, are kind of like old in a sense, and like new research kind of looks at like how to learn from images in different ways. I mean, convolution is still one of the main workhorse for things like images, but you'll see them in other like different data types as well. But yeah, like it's a really fast-moving area. So 2012, not that long ago, but might as well be a long time ago in terms of the kinds of progress that's been made. Yeah, there's this also kind of mention of using similar ideas with audio, but transforming that audio into spectrogram, which, if you know anything about that, transforms it into a kind of 2D frequency image, if you want to think of it that way. Right. So this is AlexNet. So just like that. All right. So even these slides now are a little bit kind of out of date, but convolutional networks are now kind of everywhere, right? So like this basic, like these kind of basic tasks of being able to recognize what's in an image, and like use representations of these images, learn from neural networks to like say what's similar to each other. Like you're seeing here, like if I like want to find things that are similar to this image, I can use neural networks to then go find all the other images who have representations that are similar to this one. And here's an example of that. A lot of these papers were published, by some of these early people. You see Jeff Hinton's names on these. Anybody recognize this name? Ilya Skaber? You may know OpenAI. So he's now basically, chief scientist over there. So you like some, the people who publish these really important papers are like kind of show up over and over again, and now are running some of these companies that are really well known for their applications of a lot of machine learning, AI. I try to avoid saying AI because it's got a lot of baggage, but not just being able to say like this object's in here, but saying where all the multiple objects are and what they are. Being able to do that, not just like kind of in this coarse way, but also like pixel by pixel, being able to say what's called like segmentation or semantic segmentation. Look at these images and say, like all these pixels are a road, these are a person, these are cars, so on and so forth. Obviously, the application of autonomous driving. There's so many like different things here, right? So like pose estimation ends up being like an application that shows up over and over again, along with like things like facial recognition. I mean, just being able to like automatically play to like the best of beyond human capability, like simple video games, and even more challenging games like Go, like we talked on the first lecture in this class. I mean, like other really fascinating and important, maybe more useful or like more impactful for human uses are things like being able to appropriately like diagnose, like in this case, can you say whether a tumor is benign or malignant, or be able to scan through massive amounts of astronomical data and locate galaxies and then classify them, say what kind of galaxies they are. Read what's on signs, be able to recognize, like pick out where whales are in like massive images of the oceans, being able to like do maps of like automatically generate maps from images, say where the roads are, say where the houses are. Being able to like take images and automatically caption them and things like that. I mean, there's just so many really cool applications that use convolutional neural networks, and always when there are images involved. And then there's like these kind of wild things that you might have seen where you can style certain images in a certain way, but there are these other ones that we'll also take a look at some point where you can get networks to kind of like they call it like hallucinating, but basically you get it to like look at regions of space and then like turn that space into like the most likely thing that's there, even though it's not there. So like certain ways of certain starting points for images might produce things like these fascinating like kind of tie-dye patterns, or things that have like structures that you recognize like buildings or whatever. And we'll look at more examples of that. But I mean, there's just so much that can be done with images now, and most of it is based on the methodology or the technology of convolutional networks. So that's what we're going to spend our time talking about today. All right. So as always, please ask questions as we go. So this is what we've been doing so far, right? So we've been taking like a CFAR image, which is a 32 width, 32 height, and 3 channels of color, depth of 3. And what we've been doing is we've been just kind of stretching that out into one long vector. 32 times 32 times 3 is 3072. We have this vector of length 3072, and then we learned a matrix that transforms that into a vector of length 10, because for CFAR 10 there are 10 classes, and we want those classes to represent, we want those scores to represent some kind of like belief about which class is in the image. And this is for a single, single layer linear classifier. Of course, we started looking last time, and in your homework you're doing multiple layers of these kind of fully connected networks. So that's the idea, right? And importantly, we have this linear operation here, which is a matrix times the input. And it's fully connected again because this matrix, it's not restricted in any way to like have any sort of any kind of structure. Basically, every entry in this matrix can be non-zero, and a non-zero entry there represents a connection from the corresponding entry in the input to the corresponding entry in the output. And so that's what we mean by fully connected. There's all this is typically, again, not sparse, there's not zero entries, and there's a connection, there's some non-zero entry there which represents a weight that can take you from part of this input to part of that output. So fully connected. But this is problematic because if you have a very large image, this input's really huge. If you have a lot of classes, then you have this huge matrix. Importantly, I sort of said this, but I never point out all the time because Kevin's here. Each row here, each row in this matrix is going to give us one of the values. Each row here corresponds to one of the values here. And it's a dot product, right? It's the dot product between the row and the input. Okay, so convolutional layers are basically, they're basically like the same thing, except you do have some constraints. You don't let it be fully connected. You actually only have connections locally around certain parts of the image. So what do we mean by that? So imagine this is one of our CFAR 10 images, right? 32 by 32 by 3. Okay, and instead of stretching it out, we're going to keep it in this. We're going to keep it in this format because this is like a natural format for an image. And then what we're going to do is we're going to have our parameters W, but instead of it being, again, this like full matrix, it's going to be this small, what we call a filter. Okay? And small in the sense that, in this example, this thing is 5 by 5 by 3. So 3 matching the number of channels we have here, but 5 is much smaller than 32 here. So we have this, and these are weights. Like I know it looks like just like a prism, but it's think of it as like containing 75 different parameters here. Weights W. 5 times 5 times 3. And what we're going to do here is we're going to basically take this filter and sort of slide it like around this image, taking dot products everywhere we go. That's going to give us a number. That number is going to be part of our output. And what we're going to get in our output is a whole bunch of numbers arranged spatially like this. What the output dimensions are depend on how we do this kind of sliding, but one number for every time we kind of lay that filter down here and calculate a number. And that's the idea of convolution, and it's actually not truly a convolution if you know your applied math, but it's close to it. Right, so I would say this. The depths match. The reason the depths match is when we kind of slide this thing, every position that it's in, there's always going to be a set of parameters for each kind of slice through for each of these channels. And the dot product we're going to do here is just going to be over like entry-wise, right? Like all the weights all the matching, like entry-wise or like, you know, in the same position, all the numbers that kind of relate to each other, just if we multiply them together, then we'll add them all up to the end and get a single number. And that's what this is showing you here. So it's like, you know, this is overlaid here somewhere. There's going to be 5 input values here, 5 input values, you know, 5 by 5 by 3 input values. Those are going to correspond with 5 by 5 by 3 parameters. We're going to do all those products. So it's basically it is a kind of dot product. So the weights times this portion of the input, and then we would add a bias value to that, giving us one more parameter, and that's going to be a single number, and that's going to correspond to, you know, an output to the entry and the output here. And so once we do all that sliding, let's say like we started up here in this corner here, like, you know, perfectly, like not running out to the left or up above, just matching with the first 5 by 5 structure here, or subset here, and then I just kind of move, like let's say I just move to the right here, one, you know, pixel or one set of entries at a time. What I get is, because this is 5 by 5, I'm going to end up doing, I'm going to be able to slide that 28 different times, right? 32, because it's 5 by 5, like, basically, like, there's like, I start 3, like the center of this thing is kind of 3 in here, and a 3 in the side, so we're missing, like, entries for anything in the 2 columns here or in the 2 rows here. And that's why it ends up being 28 by 28. And it's just one number there, right? Even though this has got 3 channels and our filter has 3 channels, because I'm always collapsing it down to one number, this filter just gives us like one kind of 28 by 28 slice. Yeah.
So I can like kind of see what the operation is doing visually.
Yeah.
What is it? What is that operation? I guess.
Yeah, it's a dot product.
I guess in like a like taking the matrix to be like a linear transformation, like both these matrices to be linear transformations.
It's a dot product. So, it's a dot product, and the sliding is a convolution with this kernel. Right. So a convolution is you typically see it as an integral over like all your configuration space. So what you're doing is you're moving that's essentially moving that kernel, you know, over your input, and at every location where that can be, you get a value, which is the output of the integral. That's what this is in a discrete sense.
So it's like a discrete integral.
Yeah, it's like a discrete. It's a summation. It's a dot product. I know you don't believe me yet, but you will. It's a dot product. Each one of these is a dot product, and then like as I'm sliding it over, it's like, it's like and the convolution, you basically have 2 parameters that say where the kernel is and where the input is, and then that gives you a value. It's the same thing here. Where's the kernel? Where's the input? Then gives you a value. The important part here is that you get this output that is 28 by 28 by 1. And this says activation map here. That's fine, you can say activation map. Really, we reserve the word activation map for after we apply the nonlinear activations to each one of these entries here. Like, that's typically what we want to reserve that for. But and usually we think of these as like, this kind of combination of doing a convolutional layer and then applying, one or more normalization layers and then activation. But anyways, the point is that like you get this as an output. So one filter applied to this input gives you kind of this 28 by 28 by 1, so just like this one slice. And we can have as many filters as we want, right? Yeah.
Yeah. So is the overlapping always fixed, or is it a hyperparameter as well?
Is the what?
The overlapping. Let's say one convolution filter I put, and then I overlap with the second convolution filter, and I go on through the row, right? So that overlapping between 2 filters that we do, is it a hyperparameter, or in this case it's 4, I assume. The overlap is 4 between 2 filters. So So is it a hyperparameter or is it fixed for like everything?
Let me see if I understand. So, like the fact that we started this thing in the corner here, yeah, that's a kind of hyperparameter that you choose. Usually, yeah, you can choose. There's a we'll get there. We'll see different choices that you can make. But there are different choices. You can kind of decide where you want these things to start, which means that if these things like start where it's kind of overhanging the image, you need to make a decision about like, well, what should happen in that overhang position. Usually, you do what's called zero padding. You just imagine there being extra zeros. It contributes nothing to the product, but allows you to say have the output be 32 by 32. If I were to like say pad these with a 5 by 5 filter or kernel, pad these by two rows or two columns of zeros all the way around. And then other hyperparameters are things like I don't have to slide by 1. I can slide by 2 or 3 or something like that. Yeah. So we'll get to that. We'll get to that. That's called a stride. There are other kinds of hyperparameters here that you choose. It's part of the architecture. Yeah. Good question. So is there another question? Yeah.
Does this apply to image size? Is always fixed? It's always 32 by 32. We're never gonna change it.
Yeah, that's a great question. So typically, when you're like training a model, you'll pick an input size and you'll basically stick with it. So like in CFAR 10, it's prepared so that everything's 32 by 32. But like Imagenet is not that way. And the decision that's made for Imagenet is that you resize the images to be all of the same size. And that's got its own kind of interesting aspect to it.
So if you have a really big image, you have that squash down.
Yeah, if you have a small one, or like, if it's rectangular, the expectation is squared, and you have to change that. But there's more to it than that, and it has to do with data augmentation. But again, we'll talk about those kinds of things. But yeah, typically the way you approach this is that you have a fixed input size. It turns out that you can get away with usually like running inference or like doing a forward pass on like a test image with something of a different size. There are things to think about with that, but you can imagine doing that. All it really does is gives you different sizes for your activation maps, but like the operations, like the convolutional operations, are still well defined. But don't worry about it too much. Just think about this as being fixed input size. So, go ahead.
So could another reason for padding be because the edge pixels won't be that much utilized in the activation map? Because those will only be considered for the edge activation. And
if you pad it and you make it all zeros, then it doesn't contribute anything to the dot product that you do when you include something from the zero to it. But that's not the only thing you could do for padding. It's the most typical thing to do. But you could do things like mirroring the image, like these two things, like that kind of sometimes shows up. And there's other things you could do, but it's typical to zero pad. I don't know if that was your question, but.
Sort of, but I just think that in this way, the edge pixels won't have as much effect as other pixels because they will be considered in more activations.
Yeah, so in this setup right here, you're right that the edge pixels here can contribute less to the they're involved in less dot products for the output than the central ones. And then the zero padding changes that and allows them to contribute as many. And that's also why you get you can make this have 32 by 32 output by doing the padding. But I'm not sure if that was your point either. But you're right, in this case, the edge pixels kind of contribute less to the overall output. Anyways, the point I'm trying to get to here is that for every filter, they're also called kernels, for every filter, you're going to get one of these 28 by 28 by 1 outputs. And what this is doing is for each one of these filters, you're getting another channel here. So this depth dimension we often call channel, and usually you're going to have many of these. And these, if you think about this, kind of plays the role of the rows in your fully connected, in the matrix for your fully connected layers, right? So think of each one of these as a row. It's producing kind of one of these slices, and then each row gives you another slice. And this is how we build up kind of like different sets of features for each convolutional layer. And we've shown some pictures of it already, but we'll look at some more of these. Like, in these early layers, different filters sort of correspond to very simple kinds of spatial patterns that you would see in an image. As you go further down into the network, you actually get much more complicated things, and they tend to be things like face detectors and things like that. But we'll get to some of that and try to build that intuition. But right now, what's important is for each one of these 5 by 5 by 3 filters, we get one more slice of our output, and we build up the activation maps in that way with different filters. Think of those as corresponding to the rows of the matrix in the fully connected layer. Right, so we can do this one slide. So we have 6 filters, then we're going to get an output that's 28 by 28 by 6. And these things, we'll just throw this word around a lot. These things are just known as tensors, right? So a matrix is this two-way structure. I want to get away from saying two-dimensional, but this kind of two-way structure. We'll often be working with order 3 tensors because they're going to be output from convolutional layers of an existing order 3 tensor. And so we have kind of 3 different ways here in these tensors. But the dimensions of them differ. And we can make this depth, we can make this as this depth, the number of channels here, we can make it as large as we want. We just got to keep adding filters to learn that in this convolutional layer. Right, so what does a convolutional layer do? It takes a tensor like this, like a 3-way tensor like this, and it transforms it into another 3-way tensor. Yeah?
I just want to clarify, so these 6 things over here, did each one of them come from a different, smaller matrix? Or is
each one of these came from a different one of these right here. But one of these, a different filter. Okay. Yep. Each filter is generating a different slice, a different channel. That's how we get the channels. If we wanted 7, we learn another filter. If we want 128, well, we just keep going, right? Right, and so what are convolutional networks, or CNNs or convnets? They're basically just like layers of doing this, right? Where we do that kind of, we pick a number of filters, we do the convolutional operation. We'll follow that up with any number of kind of possible normalizations or something like that, or we follow it up with at some point we follow that up with some kind of nonlinear activation. Typically, the rectified linear unit or ReLU, as we talked about today. And then that's going to be your output. So this is your activation map, or sometimes called a feature map. Probably more often called a feature map. But it's just, what has this done? This has just transformed this tensor from 32 by 32 by 3 to this tensor 28 by 28 by 6. This is why is TensorFlow called TensorFlow? Well, it's basically a way of flowing tensors through a computation graph. You're transforming tensors from one stage to the next. All the question here.
So these 6 filters, the difference between them would be the weights you activated?
Yeah, they're going to have a different set of weights, right? And we'll really quickly get to some examples of what you can visualize these filters because they're also of depth 3. And just for the first layer, the next layer is a little bit harder to think about. But for that first layer, and they're you'll see, they're like edge detectors, they're like texture detectors or things like that.
Why 6 instead of 3?
It's an architectural choice. You can think of it as like a hyperparameter. If you start thinking of it as hyperparameters, you have you have like many hyperparameters.
But you're doing it once for each channel, right?
Doing it once for each filter, right? Each filter has a depth of 3, and it produces one of the channel of the 6 channels here, because we picked 6 filters. We have 6 because we picked 6 filters. We could have picked this to be 128, 256. We could have picked it to be 1. I don't know. You know, it's one of those things. Like just you make a decision here, and like you'll see like you'll see like there's like a lot of as we go through like existing networks that are really popular that are useful in a lot of different settings. There's a kind of logic to like that's how you go from the input to like different sets of channels as you move through the different convolutional layers.
So if you had like one little box here, you'd have six of these convolutions looking at that little box at like the top left corner.
Yeah, there's like 6 of them. Yeah.
So how do we know they're not all just going to learn the same thing? And
yeah, that's a great question. They could learn the same thing if you have a really simple problem. Typically, they don't because you're typically going to use very very complex problems to do. But yeah, like if so you can think of it this way: if your network has more what's known as capacity than your data set has for the task, then yeah, these can become redundant. But remember, what this is trying to do is it's trying to adjust all these parameters so that it can do the very best it can on the task given your loss function. So there's incentive built into this for these not to be the same. If by not being the same, they can do like the network can do the task better.
is this where like random when you initialize to random numbers, you try to get the balls to roll into a different hole or something?
I mean, I guess you can think of it that way, but really it's just the initialization is really just so you can get the gradients can start to like there's enough gradient information to when you start them. They'll just on their own they will not be the same filters usually. I mean, you can pick this to be like way too large and then yeah, like they'll probably be redundant. But usually you'll pick these things and they will be anything from about redundant. You'll see it's pretty cool. Do you have questions as well?
Yeah, same question. Whether they end up being the same things.
Yeah. You don't typically that isn't the usual case because again there's an incentive. Like if there's any kind of improvement that can be gained by having a way to be different, then that will typically happen unless you find yourself into a weird space where like the gradients will propagate back to those to get that information to those weights. Yep. So you just kind of keep doing this and keep doing this and keep doing this. And that's a convolutional neural network. Notice that the filters in this next layer have to have a different depth. They can have the same spatial extent. You can actually change this too. Like this could now be 3 by 3. But in particular, this has to match the depth of your feature map, the input in this case, to this next layer. Because again, what you're trying to do, and like, there's ways that we actually don't follow that. There's kinds of convolutions that don't respect that. But in general, they do respect that because what you need is to be able every time you lay that filter, over in this case, the input to this new layer, you want there to be this equal amount of depth so that there's a weight for every entry there. So that when you do that dot product operation, it makes sense that way. Okay. Right. So, like, what do these look like? So we haven't talked about this yet, but this is a different kind of. This is not AlexNet, but it's kind of like AlexNet. It's a very simplified kind of convolutional net called BGG. And this is the first convolutional layer. So these are the filters in the first convolutional layer. Notice that there's 64 of these, I think. Yeah, 8 by 8. So they're just laid out this way, but that means that we learned 64 filters in that first convolutional layer. And this is what they look like. If you're to visualize them, this is what they look like. So just take a look, right? So some of these are just solid colors, right? So when you're sort of passing it over the image, and like you mostly have like a purple or pink or orange or whatever area there, those two are going to be very, like that input and that filter are going to be very aligned. There's going to be a very large dot product in that case. So the output sort of indicates, right, that like, hey, there's a pink patch or a purple patch or a blue patch. Excuse me. So like, yeah, there's white and black ones as well. Sorry, man. I also got the direction. So that's like those solid colors. You'll see that you have these like what are called edge detectors. So these alternating patterns of white and black are all over the place, but sometimes you'll see that it's not just white and black, like here's white and red. And again, if you do a dot product of this with a part of the image where there is a similar pattern, then the output's going to be large, indicating that you have this kind of a pattern in this part of the image. And so forth. There's like, so that, there's horizontal versions of this, there's vertical versions, there's diagonal versions, going in different diagonal directions. They differ a little bit in terms of like, actually being like, like the some of the details in the edge detection. But in general, you have these kinds of detectors. So they're very simple kinds of patterns that are being used to say like what's going on in this part of the image. Okay. Now what's being done here is at other layers of the network. So this was the first convolutional layer. Now like go to the third convolutional layer. They're trying to help you visualize what might be happening in these things. So, this is we have way more filters than just 3 here, but this is a way of sort of what's done here is a PCA to get you down to 3, like the 3 dimensions that contain the most variance within the filters. And so now you're visualizing these guys, and you can see that these are far more complex, right? So there's still a lot of 3 layers in. There's still a lot of like edge kinds of things, but notice how the colors are far more kind of combined and kind of mashed together, and where the edges are far more complex, right? Like you see, this is kind of like a triangle kind of pointed up. There's like this kind of purple here, yellow and green on this side, purple, whatever. So this is like detecting things that look a little bit more like that. Why the colors? It's kind of hard sometimes to say, but like for whatever reason, arrangements like this seem to help in doing the complete task. And then you go even deeper and you get these more complex patterns. I'll have another way of visualizing this, basically by asking what kinds of input cause like different neurons in the output, the different output entries to be active, and you'll see really cool things like you'll start to recognize things like complex textures. In fabric is versus solid patterns in fabric. Face detectors, like body detectors, things like that. But they're all being built out of these kind of crazy filters.
Why does some of them look like they're just noise?
I don't know. It's a good question. It could be that that there wasn't enough gradient to to separate those things out. I don't really know the answer to that. It's a good question, though. It could be your project at the end of the semester. Figure out why those filters look like noise. So anyways, this is the kinds of things that these networks start to learn. And the idea is that from simple kind of spatial pattern detectors, you can build up far more complex spatial pattern detectors. Yeah, this is saying the same sort of thing. And how there's some similarity in, if anybody does neuroscience, like you'll know something about how like the visual system, especially like the primary visual cortex and some of the early cells, how they are more or less like they act in very similar ways in terms of being like edge detectors that are tuned to certain angles of the edges, also like continuity of the edges, things like that. It's a pretty complicated thing, but pretty interesting that there are some direct similarities between what early parts of the visual system are doing in terms of like representing the input and how that's similar to like what's being learned by these convolutional networks. These are examples of activation maps. What they might look like. As you look at different parts of the image. No color here, just like trying to indicate something about the kinds of like textural patterns that you might see there. This is an explanation about like why this looks like why we call this convolution. It sort of looks like the thing that we're doing sort of looks like this this operation here, which we were talking about earlier, this sort of discrete integral, or which is a sum. Not totally important here to understand all that, but that's where the word comes from. Cool. So like, what happens in these networks, right? So you have like an initial convolutional layer, and then you apply. Sorry, I should say this is a very, the network being represented here is a very typical kind of network called a BGG. So we're gonna in a couple of lectures we're gonna go through what exactly that is. But you have an initial convolutional layer is applied, then a random activation, and then convolutional layers and random activation, and there's pooling, which actually kind of reduces the spatial extent of these feature maps, and then repeat convolutional layer activation, pooling, repeat, pooling. Eventually, because of this pooling, and also some decisions about, how the convolutions are done, the actual values here, or the number of pixels here, like in this case it's 4 by 4, and at that point you flatten those out, and then you have a couple of fully connected layers, and then that would then produce a score for the different classes in a classification problem. So what we have now is a score function like we had at the beginning for just linear, a linear score function, but now we have a very nonlinear score function. And it's just built up out of these operations. You can't see it super well here if you like look at the slides that are up on Canvas now. You can kind of see this, but like these, if you look at again, these are feature maps. So if you look at these, you can kind of see this in these early layers. It still looks like you can still kind of see that there's a car here. I don't know if you can kind of see that from your vantage point. You can kind of see there's a car here, right? Because like all you're doing, whether it's 5 by 5 or 3 by 3 or maybe a bit larger, you're just kind of replacing, a pixel that's here, 5 by 5, with, these 25 pixels with 1 pixel. And, because the car it extends over hundreds of pixels, doing that transformation still preserves a lot of the spatial structure of the original input. So you can kind of see that there's a car there. Then when you apply ReLU, right, then like a lot of everything that's negative in the image kind of goes to 0, and then you're left with like certain parts of it. So if you notice here, like already what's happening is like this filter, this filter right here that produced this output after applying the ReLU, there's basically just like this bright hood that's left over, right? And so somehow just focused on the hood. If you look at some of these other ones, there's focusing on like the body of the car, or like this is kind of focusing on like the surrounding, like below and around the car. You just kind of go through and you kind of see that like these just in that first layer, there's some focus on different parts of this, and then now you apply the next convolutional layer and to that, and you're going to see that there's you get something else. And you're going to apply, the regular, you can kind of see, again, like where there's non-zero output. And you just keep kind of going. The image is being reduced in spatial extent. And what you're getting is like more and more abstract kind of descriptions of something about what's in this image. And those are all kind of coming together to eventually be a really excellent classifier that's going to say that like this is most likely going to be a car. Yeah.
What does pooling layer do?
What's that?
What does pooling layer do?
Yeah, I haven't really described it yet, but it's basically a way of reducing the spatial extent of the feature map. So a typical, there's a couple different kinds of pooling, and again, Reggie's going to spend more time with this in just a second. But you basically like will take, it's called pooling because you'll take like, say like 4 pixels in a 2x2 grid, and you replace that with 1 pixel. And that's reducing the spatial extent of the by 2 on both the for height and width. And yeah, I mean that's and there's like, well, how do you do that? Well, you can average the values that are there. You take the maximum. These are like kind of typical things. But again, it's like it's a choice you make for the architecture, whether you're going to average and max or even have a pooling layer or whatever. But that's really what's happening, right? So just layer by layer, this is just it's processing this image in such a way that like like whatever this is right here, like the fact that there's like a very large activation here in this part of this final kind of 4x4 image is saying something. It's saying something about this being a car, hopefully, right? And that's what all it is. And so it's hard to interpret just by kind of talking through it, but that's what's happening. Each one of those, each one of these filters and each one of these layers kind of combining, working together to get this final output, and then goes into fully connected layers that produces a score. And all the weights are being adjusted through the training process, the stochastic gradient descent, so that you get better and better and better at that task. It's fascinating because like at each layer it's kind of really simple to understand what's going on, but when you put it all together, it's a really a really complex operation, very nonlinear, and turns out to be quite good at these kinds of tasks. All right, how are we doing with that? Yeah. All right, so let's get into this just a little bit more here. So this operation we've been talking about, we're just going to describe it. Hopefully, like you got a good picture of this now. But let's say that. So we're just going to assume that whatever number of channels there are in the 7x7 input, the filter has the exact same number of channels. So what are we doing here? We're taking the 3x3 filter as represented by the green squares. We're overlaying it, in the input. And we're doing that dot product operation. That gives us a value. And then, we start to slide it, right? So here we slide to the right. We can do this dot product again. Get a different number. It's clearly there's some kind of correlation that's happening here between the numbers because the image already has spatial correlation in it, and it's the same filter you're passing over. So there's this is again why you kind of see the global structure of the car being made in that picture. But this is the idea. You just keep sliding it around. We're going to get the 5x5 output because there was 1, 2, 3, 4, 5. 5 ways we could have then we could slide it because we could slide it 5 times, moving by 1 pixel each time, without kind of going outside of a 7x7 grid. And we can do the same thing going down. So we get a 5x5 output. But we could do these things differently, like I said. So instead of moving by 1 pixel, either to the right or down or whatever, we could do that by 2, right? So I could now shift by 2. So now that filter moves over by 2 pixels, moves over by 2 pixels. In this case, it was only, I can only do that 3 times within the 7 by 7 grid. So my output is 3 in that direction and 3 in the vertical direction. So the output here is 3 by 3. Could I do a stride 3 here? Well, I can do the first stride. I can do the first stride 3. I can move it over here. But then, what would be the next stride 3? I would end up over here, and I have this overhang that we don't really know how to deal with at this point. So, we might say we can't apply this filter to a 7 by 7 input because with a stride 3 because it just doesn't produce sensible output. And you can start to think about the math here about what's going on. I have a total spatial extent of n, and for the input, and my filter extent is f. The output size is going to be n minus f divided by the stride, so how many steps I'm taking, plus 1. And if you think about what we just did, when we had 7, the input size was 7, the filter size was 3, and we had stride 1, you can see if I do this math, it comes out to be 5 in the case of stride 1, 3 in the case of stride 2. But we don't get an integer in stride 3 in this case, indicating that this would be a valid operation. Okay. So we talked about this already, but in practice, what we tend to do is we don't typically want to reduce the spatial extent of our feature maps from one layer to the other via the convolutional operation itself. We might want to do it via stride, but we don't really want it to be because the filter doesn't fit into the input size. So we all do this thing that we call padding, and how much padding you need to do depends on the size of the filter. With a 3 by 3, you typically only pad with one row or column of zeros. Because what you want to do is you want to be able to center the filter in the corner of the image. So if we do these zeros, when we do this dot product, no matter what the weight is here, because the input is 0, the product is going to be 0, and it's not going to contribute to the dot product. So product with zeros is just like a conceptual way of allowing us to do this kind of convolutional operation and preserve the input the input spatial dimensions. So now if I run this this convolutional operation with stride 1, I have 7 by 7 input. I'm getting a 7 by 7 output. And if I now do this with stride 2, let's see, yeah. If I do this with stride 2, oh no, sorry, that's not what I'm trying to say here. If my filters are different sizes, I will need to zero pad with a different number of columns or rows. So and again, it's pretty easy to see. You put this so first of all, the filters are always odd, they have an odd number of spatial extent, and that's because of just the geometry of these things, right? What you want to do is you want to take that filter, you want to put it in the corner, and that is the first. That should be the first output for the spatial map. So if this was an even number, you would have a hard time basically doing these kinds of nice operations in the end. So just conceptually, we typically work with filters of odd spatial extent. The sizing varies because the math works out nicely. So if it's 5, you have 0 pad 2. If it's 7, and so forth, right? You just kind of stick it in the corner and see how many zero padding, how many columns and rows you would need to zero padding. Questions on any of that so far? Pretty simple conceptual stuff. Was there a question? No. Yeah, so if we, so this is just kind of saying, this slide here is saying the same thing I was saying earlier. If we don't do that kind of zero padding, then every time you do a convolutional layer, you like really quickly are reducing the spatial extent of the feature maps, and that you don't typically want that. Like sometimes you do. That's why we have pooling layers and things like that. That's why we do things with Stripe too. And as we look through, different examples of like well-used convolutional networks, you'll see that kind of design choices there. But you never see a choice where the way you do is you reduce the spatial extent is by like not zero padding. Okay, so yeah, so let's just go through a couple examples here. Our input's 32 by 32 by 3, and we have 10 5 by 5 filters, and we're striding with, we have a stride of 1, so we're just moving 1 pixel at a time, and we have a pad of 2, so 2 columns or rows of zeros. What's the output such?
32 by 32 by 10.
Yeah. So because it's stride 1 and pad 2, you know you're going to get the same like spatial extent, 32 by 32. And like the 5 by 5 here, really the only one I kind of think about here is just we have padding. And we do because 5 by 5 requires there to be 2 to put a 5 by 5 filter with the center in the corners. And then how many channels in the output? It's just how many filters we have. So it should be 32 by 32 by 10. Yep. Cool. So here's a question. So how many parameters in this layer?
Okay, sorry, just a question.
Yeah.
I was kind of confused about this earlier, I didn't ask.
Yeah.
So the third dimension, like by 3, or not dimension, like like how that seems to have no effect upon the output layer. So how's it even being used? Like it seems like we're just convolving this with like
The reason is that we make a choice and we say our filters are all going to have whatever this number is in the input, whatever this number of channels is, all of our filters are going to have the same that same depth.
Okay.
And so when we do a dot product, it's just going to match perfectly, right? Like there's going to be a weight for every kind of channel or slice. There's going to be like a corresponding weight in the filter for that slice. And so when we do the dot product, it just kind of combines it all together.
Okay.
Yeah, cool. Yeah. So how many parameters in this layer?
32 by 32 by 10 by 25.
Not 32s. That has to do with input. How many parameters are in this? Where are our parameters? Our parameters are in the filters. Right? So, yeah, so the weights, the parameters, those are, I'm using those interchangeably. I'm using parameters here because you sometimes think of parameters as both weights and biases. So I'm kind of including all those, although we totally, all the time, conflate those ideas. But so where are all the parameters? Well, each one of these filters has 25 weights plus a bias term, right? So 26. And I have 10 of those. Right? So I got 260, right? Oh, sorry. 25. I got the 3. My bad. So 25, but I have 3 channels. So 25, so 5 times 5 times 3 is 75. And I have the bias, I have 76. I have 10 of those. So 760. Does that make sense? So, if I were, what would like the corresponding,
But don't you have to do it for each?
Nope. Yeah, I do it for each, but that's just like, that's the output size. That's not the number of parameters, right? The parameters has to do for all these filters. We use that to then produce an output size. That's something different. So like, the size of the feature map and the number of parameters are different, and it has to do with, so the output size has to do with like the input size plus the details around the filter size, the stride, the pattern. But for the number of parameters, it has to do just with how many filters you have, the size of those filters, which in this case are 5 by 5 by 3, and then the number of those filters. So giving us 160. So Yeah, so the question I was going to ask is, so what would the equivalent, how many parameters would the equivalent fully connected layer have?
So it'd be 32 times 32 times.
So 32 times 3 would be 3072, we've seen a bunch of times. And then there's, if you think of the filters as rows in the matrix, that's like, there's 10 of those rows, so the matrix would be 3072 by, or 10 by 3072, so 30,720, and then we have the biases for each of those. So we'd add, we'd add every 10 additional numbers there for each one of the rows. So let's say 30,730, right? So there's, in a fully connected layer, corresponding with input of this size and output of this size, you'd have something on the order of 30,000 parameters. When we do convolutional layers, we have 2 orders of magnitude less parameters, right? So this is what convolutional layers are for. They are for being able to learn parameters that help you transform the image in such a way that you'll learn the task, but we're doing it with far fewer parameters, orders of magnitude less parameters. So that this becomes a much more efficient learning task. Yeah. There's a bunch of math here that you can convince yourself of, okay? Yeah, what are common ways of doing this? So you typically, I don't know if you noticed this yet, but most things come in powers of 2 in neural networks. There are some interesting reasons for that. It's mostly historical at this point. But you'll typically see in convolutional networks, number of filters that you'll have will be a power of 2. And then choices for like the filter size, the stride, and padding. You almost always pad with so that you don't reduce the spatial extent. Sometimes you might choose to have a stride larger than 1 if you want to use that convolution to reduce the spatial extent. So you do that through the stride. And sometimes you might even have a convolutional filter that has a spatial extent of 1. So it's basically just like a column filter going through your image. Those are called 1-by-1 convolutions. They're used all the time in modern networks. It might seem weird, but you'll see why when we get to some examples of this. And there you don't use any pattern because you can put that right in the corner, no problem. Yeah, 1-by-1 convolutions make sense. This is the typical way of using them, is typically to reduce the number of channels in a feature. Do 1-by-1 convolutions and then to reduce that, and you'll see they're very useful. They show up all over the place, and they're mainly used to do that kind of thing. All right, questions so far. I guess we're at 5. We're not quite done with the slides, but I think we're mostly done here. This is just like, hey, look, this kind of looks like grain. You can look at that in the. I already did this. Sorry, I have a slide. This was talking about again, like what the fully how many parameters do the fully connected layers. Well, so next time we'll start with we'll start at the end of these slides here. Just talk quickly about tooling and other forms of sampling there, and then we'll be done. Okay, so happy to take questions.